Hey everybody, my name is Mitch and I'm a member of the MSP 430 applications team at Texas Instruments. Thank you all for joining today. We're going to explore how you can have your cake and eat it too by utilizing analog solutions within our microcontrollers. I don't know about you guys, but I love cake, like a lot. But actually baking the cake, well, that's a totally different story. You could go out and spend hours buying the eggs, flour, the butter, the milk, and the rest of the ingredients for it, or you can save time and money by getting boxed cake mix and having a cake ready in 30 minutes. I'm a big fan of the latter. The same idea can now be applied to today's technological designs. External analog components such as op-amps and DACs come with challenges of taking up valuable space on your PCB and increasing bill of materials costs. But what if I told you that TI had several devices available today that can help alleviate these burdens? Yep, making our cakes just got a whole lot easier. More challenges are being met in many of today's applications. Space limitation and bill of materials control call for small component sizes and compact designs. Extended temperature ranges are being required in more systems. Easy migration and upgrade is also considered as a key benefit in MCU-based system designs. The FR2355 microcontroller from TI integrates configurable signal chain elements, including a 12-bit ADC, comparators, multiple operational amplifiers with programmable gain, and digital to analog converters that will provide flexibility within a system design. By leveraging these configurable signal chain elements, developers can reduce PCB size and BOM costs for their applications. This microcontroller supports extended operating temperatures of up to 105 C, which allows for high temperature applications such as smoke detectors, sensor transmitters, circuit breakers, and many others. As an extension of the MSP 430 FRAM value line portfolio, the FR2355 microcontroller adds 32 kilobytes of memory with up to 24 MHz CPU speed to the family, providing more options for cost-sensitive applications. Let's take a deeper look into what is included within the FR2355 device. This device belongs to the FR235X family. Throughout this presentation, I'll be referring to the FR2355 device, but I want to point out that the rest of the devices in this family have the same peripherals. Only the memory options vary. The FR2355 device has 32 kilobytes of FRAM and 4 kilobytes of RAM. The configurable signal chain elements include 2 comparators, a 12-bit SAR ADC with 12 channels, and 4 smart analog combo blocks. Each block includes a configurable op-amp with optional programmable gain and a configurable 12-bit digital to analog converter. In addition, the device has a 32-bit multiplier, 4 16-bit timers, and 4 communication channels. 3 packages are supported, including a 48-pin LQFP, a 40-pin VQFN, and a 38-pin TSOP. Evaluation tools include a 48-pin target socket board and a launchpad. Check out the links to these evaluation tools and other references when we send out these slides after the presentation. Now that we know a bit more about the FR2355 device, let's explore these configurable signal chain elements we call the Smart Analog Combo, or SAC for short. The Smart Analog Combo is a peripheral integrated within the microcontroller that allows you to configure op-amps and 12-bit DACs into any configuration of your choosing. There are 4 op-amps, each with programmable gain, and 4 DACs embedded in the microcontroller. Designers will immediately benefit from the flexibility of the peripheral and also the cost savings it provides. Let's take a deeper look at the flexibility of the peripheral. There are 2 device families that offer SAC configuration, the FR231X and the previously mentioned FR235X families. The Level 1 or L1 configuration is available on FR231X devices and comes with an integrated op-amp that supports rail-to-rail inputs and outputs and has multiple input signal selections. The L3 configuration is available on FR23-5X devices and comes with 4 op-amps with programmable gain and 4 12-bit DACs. The L3 op-amps also support rail-to-rail inputs and outputs with multiple input selections. The PGA can be configured to provide gains of up to 33x, and the 12-bit DAC also has multiple configuration options that can be configured by the user. The box outlines one of the 4 smart analog combo blocks embedded within the FR23-5X microcontrollers. You can configure each of the 4 blocks in any configuration of your choosing, including general purpose mode, buffer mode, non-inverting or inverting configurations, or DAC mode. You can also cascade the blocks into each other if you wish. The flexibility of this peripheral will benefit any application where analog signal conditioning or analog output is needed. Some specific applications that require this analog signal chain are smoke detectors, gas or PM 2.5 detectors, current loop transmitters, and many more. Wouldn't it be nice if we could taste our cake before baking it? Well, good news, folks. We have a SPICE model that allows you to test your designs before making any hardware. I'm going to show you how to simulate one of our SAC Level 1 devices. Let's take a look at where to find these resources and how to use them. First, we're going to want to download Tina. Tina is a powerful circuit design and simulation tool from TI. It provides all the conventional DC, transient, and frequency domain analysis of SPICE and much more. Check out the links provided to download Tina and get started quickly. We currently have a SPICE model for the FR2311 microcontroller, which is a Level 1 device, available for download on our website. On the FR2311 home page, navigate to the Tools and Software tab, then navigate to the Model section. There you can download the Tina SPICE model for the FR2311 device. The SPICE model for the FR2355 device is coming soon. Now that we have Tina and the FR2311 model downloaded, let's start a simulation. First, we want to open Tina and insert the FR2311 macro into the circuit workspace. You can do this by clicking on Insert, then Macro, and then navigating to where you downloaded the FR2311 macro. Click on the .tsm file when you locate it and drag and drop the macro into your workspace. Next, add your passive components to your circuit. In this example, I have an inverting configuration with a gain of 2. Time to simulate. Click on Analysis and then select what kind of analysis you want to do. For this example, I will do a transient analysis. The simulation gives us a plot of the input signal in green overlaid with the output signal in red. Tina is a flexible tool that can be used to simulate countless numbers of circuit designs. Feel free to explore how this tool can help you test your design. Alright, now for the fun stuff. Now that we know what the Smart Analog Combo peripheral is, let's dive into some different configurations and applications. The configurable signal chain elements within the Smart Analog Combo can be configured in many different ways. We can configure it in general purpose mode, which gives us access to the op-amp only and bypasses the DAC and the PGA. This is useful if we want to customize our op-amp circuit with external passive components. Maybe we need to buffer analog signals and provide some impedance protection. We can configure the SAC peripheral in buffer mode for this. Non-inverting and inverting gain configurations are also easy to implement. These can be useful to amplify analog signals for ADC sampling. DAC mode allows us to provide bias voltages or generate audio signals. Multiple cascaded gain stages are also easily configurable. Keep in mind that we have 4 of these SAC blocks within the device. This means that any combination of these configurations is possible without needing external analog components. Let's go deeper into the DAC mode and cascaded non-inverting configurations. Here's how to configure the Smart Analog Combo in a DAC configuration. We can configure the op-amp as a buffer and feed the DAC signal through it. We can use this configuration in several ways depending on the application. Maybe we want to control transistors with the DC voltage set by the DAC. Or maybe we want to generate a signal with the DAC like a sine or sawtooth wave and drive it as an audio signal. The register settings for this configuration can be seen on the left. Now we have 2 out of the 4 smart analog combo blocks cascaded into each other. Both blocks are in non-inverting configurations. Keep in mind that inverting configurations are also possible on both blocks. The smart analog combo makes it easy to implement multiple gain stages within the microcontroller. Before we continue to further explore the smart analog combo, I want to point out some development tools that are available. There are 2 hardware tools users can use to evaluate the FR235X devices and quickly begin development. The Launchpad features the FR2355 device and includes 2 push buttons, 2 LEDs, an ambient light sensor that can be configured with the smart analog combo, and a Grove connector for external Grove sensors. Users also have the option to connect booster packs to it as well. If you need access to all of the pins on the device, the Target Socket board allows this flexibility. Both boards can be ordered in the links provided. The cool thing about the Launchpad is that it comes with an out-of-box demo that allows you to quickly evaluate the smart analog combo and configure it on the fly. Let's check this out. Okay, so to access the demo, we can click on the Launchpad link given in the last slide. When we click that link, we'll be brought to this page, and from here we can click on the download the out-of-box demo GUI link. When we click that, we'll be brought to the demo. So this demo is a great, quick and easy way to evaluate the smart analog combo and just see kind of what it can do right off the bat. Right now, I'm going to set our input signal source to the internal DAC. That's because I'm going to generate all of our input signals internally from our DAC. So this block diagram is going to show us how we currently have the smart analog combo configured within our device. So right now I have one smart analog combo block configured in a DAC mode configuration, and then I have a second smart analog combo block configured in a non-inverting gain configuration. This top block up here is going to show us what our DAC input signal is and what that looks like, and then the bottom box here is going to show us our real-time ADC measurement, and this is our real-time output from the analog signal chain. So right now we can see that I have the DAC configured to give us a sine input signal going into the non-inverting stage. So I have it configured as a sine wave, a frequency of 2 Hertz, and a signal amplitude of 0.4. I can change our input signal right on the fly. Maybe we want to give it 4 Hertz or make it 8 Hertz. And we can see that our output is changing in real time as well. So maybe we want to change the gain right on the fly. I can change this to 3. I can back this all the way back down to 1. And maybe we don't even want a sine wave. We can choose from sine waves, square waves, and sawtooth waves. So let's see what happens when I give it a square wave input. So we can see right now the gain's 1, so our output's going to look just like our input. But I can just give it gain right on the fly just like that. So that's pretty cool. We can literally change this right on the fly just like that. Maybe we want to change our op-amp mode. So right now I have it in a non-inverting gain configuration, but let's change it to inverting. Cool. Let's give it a little bit of gain. So we can see now that we are providing a gain of 2 right now, but we're also inverting the signal. You can see that when you compare the peaks. If I go back to a sine wave, it may be, yeah. So we're still inverting the signals. So that's pretty cool. This is a really quick and easy way to just see what the smart analog combo can do, and it allows you to configure it really quickly. But maybe we are more interested in applying an external signal to the peripheral instead of generating our signals internally with the DAC. So we can do this as well. The way we'll do this, I'm going to change the input signal source. I'm going to change this to a non-inverting signal source. We can disregard this. This is really only useful when we have this configured, our input signal source configured for our DAC. But right now, notice that our block diagram changed. We don't have a DAC mode configuration because we are providing a signal externally, just directly to our non-inverting configuration right here. So we only have one smart analog combo block enabled, and externally on my board I have a function generator that I have connected to the launch pad, and I have it connected like this. And I will go ahead and turn on that function generator, and we'll see what kind of output we get. Cool, so you can see that I'm providing an external sawtooth signal directly to my board. This is with the function generator. So it has a pretty low amplitude, but I can give it gain right on the fly, just like that. So yeah, so this is an example of how we can also just test the smart analog combo with an external signal. So yeah, so this demo is pretty useful. It's really good to test internal signals if you want to see, how do I generate internal signals with the DAC and then provide different gain stages to it, or if you just want to provide your own external signals to the peripheral, you can do that as well. Now that we know the ins and outs of the smart analog combo, let's see how we can leverage it in some applications. Here we have a smoke detector that incorporates a DC measurement design. In this type of design, an LED will emit light and the photodiode will output a current based on how much light it detects. When smoke is present, it will interfere with the photodiode and the LED, causing the photodiode current to change. In order to monitor this, let's configure an SAC block in a transimpedance configuration to convert the current into a voltage. Then let's amplify this voltage with our other SAC block so we can properly sample it with the ADC. There are several other types of smoke detector designs, including single and dual ray AC coupled designs. I have included diagrams for these as well at the end of the PowerPoint, which will be sent out after this presentation. Next, we have gas and PM 2.5 detectors. Similar to smoke detectors, an LED will emit light and we will monitor a photodiode current to detect the presence of 2.5 particles or gas, depending on the application. The photodiode current is fed into a transimpedance configuration to convert it into a voltage. Then we feed this voltage through a gain stage and monitor the ADC readings. We can also use the SAC to generate an audio signal. Simply configure an SAC block in a DAC mode configuration and add the necessary external audio components to create a functional audio circuit. Another application this peripheral can be used for is blood glucose metering. Once again, we monitor the current the test strip produces by first feeding the current into a transimpedance op-amp configuration and then providing gain to the voltage and monitoring it with the ADC. We can configure a third SAC block in a DAC configuration to generate an alarm when unsafe levels are detected. Current loop transmitters are common in industrial applications. Here, we can configure the first SAC block in a DAC configuration. Next, we feed this signal through a non-inverting gain stage to drive a transistor. We are now able to control the current level in the current loop directly from the DAC. While these applications are all possible to design with the smart analog combo, any design that deals with analog signals can benefit from this peripheral. These diagrams can be used as starting points or inspiration for your next design. Now that we have a solid grasp on what the smart analog combo is and how we can use it, let's see how we can configure it with other peripherals in the device. Maybe we want to use the smart analog combo, but we don't have a need for the comparator or the ADC. We can bypass the comparator and the ADC if we wish and route the smart analog combo directly to our output pins. Maybe we change our minds and decide that we want to feed our smart analog combo outputs into the comparator. This is easy to configure and very doable. Remember, we also have the option to cascade our smart analog combo blocks into each other. This is useful if we need to condition analog signals in multiple stages. What if we need to feed our smart analog combo output into an ADC like in some of the previous applications? We can do this as well. No hardware changes are needed. We can also configure our comparator as an input to a timer. As you can see, the configurable signal chain elements are flexible, easy to configure, and can support both simple and complex analog solutions. Alright, now that we've explored the ins and outs of the configurable signal chain elements, let's check out another benefit of the device, the ROM libraries. The FR235X and FR231X devices have two different libraries embedded in ROM, the driver library and FFT library. DriverLib provides user-friendly APIs for developing applications on MSP devices. The easy-to-use function calls keep you above the bits and bytes of the MSP hardware, allowing you to complete projects with minimal overhead. The FFT library allows users to perform fixed-point FFT transformations, both real and complex. It is a subset of the DSP-lib transform functions. The 6 DSP-lib FFT APIs that are included in ROM are listed. There is also a 2048-point complex twiddle table included in ROM. Let's take a quick look at an example of using one of the FFT functions in ROM. We start out with our original signal with two distinct frequencies. Using an FFT transformation function in ROM and some processing, we are able to extract the FFT magnitude of the signal. These ROM libraries are included with the FR235X and FR215X devices. They are compatible with both Code Composer Studio and IAR compilers. The benefits of using these ROM libraries include faster code execution and saving valuable FRAM space. These integrated ROM libraries save 20 kilobytes of FRAM storage in your device. DriverLib and DSP-lib can be downloaded in the links provided. Alright, let's wrap up this webinar by talking about the easy-to-use ecosystem for this device. Code examples for this and all other MSP devices can be found within Code Composer Studio. Code Composer Studio is an integrated development environment, or IDE, that supports TI's microcontroller and embedded processors portfolio. Code examples can be found by navigating to the Resource Explorer under the View tab. Next, click on Software and navigate to the MSP430ware folder. Energy Trace is integrated within Code Composer Studio and enables users to debug power in real time. Energy Trace can provide average current and power measurements, power profiles, and energy plots for the FR2355 device. The FR2355's enhanced MCU performance, integrated analog signal chain, integrated ROM libraries, and easy-to-use ecosystem are all features that can greatly benefit you and your next design. Thank you all very much for attending my presentation. I greatly appreciate it and I hope you enjoyed it. I'll be happy to begin taking questions now.
Great, Mitch. Thank you so much for that presentation. And now we're going to move into the question and answer portion of this webinar. I would like to encourage everyone in the audience, if you do have any questions, please make sure to submit them while we have Mitch here with us live today. If we don't get to your question, someone will follow up with you shortly. So Mitch, our first question, is there a way your demo software can display external signal being applied for comparison purpose and not dependent on output signal to determine how your external signal is?
Yes, so there is a way to be able to monitor your input directly. There's a setting in the GUI when you're choosing your input signal source. You can select a direct ADC input, and then what you'll see in the output box is whatever signal you directly provide to that input pin.
Great, okay. And our next attendee asks, They said, I have an FR6989. Is this similar or the same device as the one you were reviewing?
So this device is also in our FRM family, but there are some key differences between the two devices. They're not the same. The main differences between these two devices, the FR6989 does not have the smart analog combo peripheral integrated in it. Instead, it does have a different peripheral. We call it the ESI, or extended scan interface peripheral. For example, you can use this for rotation detection, like in flow meters. In addition to that, it also has a lot more memory to offer. The 6989 device comes in packages that support up to 128 kilobytes. And it also features a comparator and also an ADC, just like the 2355 device.
Great, okay. And how do I get started with the FR2355 device?
So the quickest way to get something up and running is for someone to go purchase the 2355 Launchpad and download the GUI demo and just get something started that way. The Launchpad, it also includes a Grove connector for different Grove sensors. So if you want to connect some type of external sensor to the Launchpad, that's another really quick way to start quickly evaluating it. And these can be accelerometers, light sensors, any kind of sensor that is provided by a seed. And another resource we have the TI Resource Explorer. That's a great place to browse for device documentation, software examples for all types of peripherals within the device. And there's also software libraries in that TI Resource Explorer. It's free within our IDE Code Composer Studio, and that's a great way to get up and running with some code. And we also do support IAR and GCC compiler as well. If that's more of your workflow, we support that. Another option is if you're familiar with working with Arduinos, the Energia IDE is also supported, and that features easy use functional APIs and libraries, and that is supported. The 2355 device is supported for that. So it's kind of a long-winded answer, but there are a lot of resources to choose from. But the quickest way to get started is to get the 2355 Launchpad and connect straight to the demo.
Great, okay. And our next attendee asked, what other applications or products can this be used for?
So any application that requires an analog signal chain can benefit from this device. As you can see from some of the examples I was giving in the presentation, a lot of current monitoring applications can benefit from it. But this device can be leveraged in a wide range of analog applications in general.
Great, okay. And our next question, how easy is it to migrate from older MSP devices?
So depending on what devices you're changing to or from, some migrations have a few more steps than others, but we have several migration guides that cover both the small and the big device migration jumps. So whatever your situation is, we do have resources that will support it.
Great, okay. And what variants of the device are available?
So of the 2355 device, the device that I focused on in this presentation, we have 4 different variants of it. The 2355 has the smart analog combo and 32 kilobytes of memory. We also have a variant, the 2353, that also features the smart analog combo, but it comes in 16 kilobytes of memory. We also have the 2155. That does not have the smart analog combo, but it does have the 32 kilobytes of memory. And then we have the 2153 that does not have the smart analog combo, but it has the 16 kilobytes of memory. And those are good package options for people that maybe don't need the smart analog combo, but they can leverage the faster CPU speed and also the extended temperature range. And as far as packages, we have several packages. We have a 48-pin LQFP option, a 40-pin VQFN option, a 38-pin TSOP option, and at the end of this month, we will have a 32-pin VQFN option, and that's going to be a 4 millimeters by 4 millimeter package size. So that'll be pretty small.
Great. Okay. And our next question: what is included in MSP 430 ware? Excuse me.
So MSP 430 ware, you're going to get a lot of code examples for the peripherals within the device. We offer those in assembly and in C. You can find smart analog combo examples. You can also find examples for all types of peripherals if you need I2C, SPI, UART, communication peripherals. Those can be found there as well. And then you'll also be able to find driver lib documentation and examples. So there's a lot of resources within MSP 430 ware to help get you started.
Great. Okay. What other MSP devices are available?
So we have a broad portfolio of over 500 devices that anyone can check out at ti.com/MSP.
Okay. And our next question: what's the max sample rate?
So the max sample rate for the ADC is 200 kilosamples per second.
Okay. And it looks like this may be our last question, unless others come in. Is the 2355 compatible to CCS for Mac OS?
Yes, the CCS is compatible with Mac OS, and the demo that I showed earlier is web-based.
Perfect. Okay. Well, it looks like that's going to do it for questions. So we'll go ahead and wrap up right here. Thank you to all of our audience members for joining us, and have a great rest of your day.